I also thank the entire seminar committee for the opportunity to talk here. I'm very excited to share some research with you. We'll touch on several topics, mostly single photon sources for applications in quantum photonics and quantum networks with high bit rates. We'll talk about fundamental speed limits for these sources, so how fast fundamentally can they operate. Some practical routes to approach these limits. We'll talk about the prospects for on-chip integration. And then if time permits, I'll also touch a little bit maybe on the optical spin readout in nitrogen vacancy centers in diamond and spin-magnon interaction. So we know that the quantum information technology is developed simultaneously across multiple different material platforms that are interesting for encoding quantum information, and many IQUIST and CQE faculty members have their research spanning across these various platforms. And perhaps the most intuitive way to classify these different platforms is by the degree to which they interact with their environment and eventually also with each other. So on one end of the spectrum, you have some systems which allow you very good control, basically from the user. You're able to make very efficient gates, and basically the interaction is very strong for these qubits with one another. On the other end of the spectrum, you have qubits that are very good for protecting information. Something which we call quantum coherence, the fact that the quantum information in the systems can be sustained for long periods of time without being lost, without producing errors. So some systems allow you better control of quantum information, some systems allow you better protection, and it's very interesting to see how these systems can interact with each other via quantum transduction so that we can sort of get best of the both worlds in terms of control and coherence. But one thing you notice is that photons occupy a very special place on this spectrum. They are virtually perhaps the best at protecting quantum information, in the sense that if a photon propagates even through a material such as an optical fiber, not very much can happen to it except loss, and quantum information in photons is protected indeed very, very well. Well, the downside is that photons don't really interact with each other, and it's really difficult to make photonic gates, logical gates based on photons. So they're really difficult objects to control on the quantum level. Because photons propagate at the speed of light, and they're, again, very immune against quantum decoherence, they're basically unbeatable candidates when it comes to realizing quantum networks for communication, for modular quantum computing, or for distributed sensing. In the past few years, we have seen spectacular demonstrations of quantum communication through satellites, clearly showing the potential for these long-distance quantum networks. Photons are also considered to realize quantum computation. Well, in this case, the main difficulty is actually to realize photonic gates. The main challenge for photonic quantum technologies, again, are these optical losses. The photon can propagate for about maybe 100 kilometers in an optical fiber before being absorbed, but that's still quite a long distance. And the other problem is that photons don't interact with each other, as I mentioned, and they interact quite weakly with matter. So there is a big problem when we want to make photonic gates. They're usually probabilistic in nature. So much so that the 2-qubit universal quantum computer that was presented 2 years ago from the Bristol group still looks like a tour de force experiment, mainly because, again, the photon generation events and the photon gates are probabilistic in nature. This non-determinism of photon generation and quantum optical operations strongly limit the performance of photonic quantum information systems. For example, because of inevitable losses, the rate of quantum communication falls exponentially with the distance. In the satellite experiments, the rates of secure communication were only a few bits per second. To some degree, this can be compensated using quantum memories and eventually quantum repeaters. And we recently saw experimental proofs, actually dazzling experiments, demonstrating memory-enhanced quantum communication. But these devices are still not very widespread. And in general, I should say that the bitrate of quantum networks have not yet reached the level at which they can be practically used for most of the intended applications. So in the meantime, while deterministic photon sources, gates, and repeaters are not widely available, we can still try to work our way to higher speeds in quantum networks by realizing a targeted and strong enhancement of light-matter interaction on the nanoscale. So this enhancement can be realized in two complementary ways. We can first work with very short pulses, which enhances the instantaneous electric field in the photons and basically enhances all the nonlinear effects and interactions that these photons can have with other objects. And also we can confine these photons to very, very small volumes, which can also lead to a dramatic increase in the electric field of the photon locally. So again, leading to the same effect that the photons will be more prone to interact. Concentrating this photonic energy in this way can be useful for many different, quantum devices, including faster and higher quality single photon emission, realizing photonic gates, and faster, efficient, and inexpensive single photon detectors. What's more, this approach has the potential to raise the operating temperature of the quantum photonic circuitry because operations can be basically performed faster. I will focus here on solid-state quantum emitter-based single photon sources, but what I will say can also be applied to other photonic quantum devices. So there are basically two classes of single photon sources. Single photon sources are the key building blocks for probably most of the photonic quantum systems. There are two classes of such single photon sources. The first class is the so-called parametric single photon sources, where you have a strong pump pulse, which produces a weak parametric signal from a nonlinear medium that has a nonlinear response, either second order nonlinearity or third order nonlinearity. But in any case, the idea is very similar. Always doesn't matter what type of material you're working with. You have a pump pulse, which produces a weak parametric signal and idler beams, having on average just a single photon or less per pulse. So these signal and idler will contain less than a photon per pulse on average. These beams are correlated in photon number. So if the signal has, for example, 1 photon, then the idler will have also 1. The challenge with these sources is that both idler and signal beams have a random number of photons, although these numbers are correlated. So you don't know how much in advance of signal and idler photons you will have, but you will always have equal number between them. So they are correlated. The best scenario for us is, of course, to have 1 photon in each signal and idler, but we could also end up with having 0, 2 photons, 3 photons. It's basically a Poissonian distribution. So the first thing we do is we have to attenuate the pump pulse in order to kill those multi-photon components. So what we want is 1 photon, but to be able to approach that limit, we want to minimize the components having 2 and 3 photons. So we have to attenuate the pump beam so that the probability of having 2 or 3 photons per pulse is negligibly small. Then by doing so, we will dramatically increase the probability of having 0 photons. But then that's where you use the correlation between the photon numbers in the signal and idler, because you can detect one of them. And if you actually have a photon in one of the modes, you're sure that you have 1 photon in the other mode. So that's how you basically kill this 0 photon component. But as a result, your photon generation becomes non-deterministic. So in advance, you will not know if you will have a photon or you won't have a photon. So there is a trade-off between the efficiency of this source, which increases with the mean photon number, but at the same time, you will have to compromise on the purity of this source, in the sense that you will start having these noise components having 2 and 3 photons at the same time. So there is this fundamental trade-off, and I should say that Paul Kwiat's group here at UIUC has made recently a very significant advance towards resolving this problem for these type of sources. And in the future, we may be able to use these multiplexing schemes to combat this trade-off and even generate photons on demand using these parametric processes. But here I will focus on the other kinds of sources that are based on quantum emitters. So the principle of emission is very different. Here you rely on a specific 2-level system or few-level quantum system, such as, for example, defect in a solid, but it could be an atom, it could be an ion, it could be anything. that has these discrete level structures and couples to optical fields. The idea is that you pump this system using a classical pump pulse coming from a laser, and then this system can only absorb one photon at a time, so it will also release only one photon at a time. So theoretically, these kind of sources are on demand, but they emit photons isotropically because they're very small, usually atomic size systems. They emit photons isotropically, and therefore it's quite difficult to collect these photons. And that's why even in these quantum emitters, you don't yet have on-demand production of single photons. That is that the photons may be actually produced on demand. You will just not collect all of them. That's one of the key difficulties. So then the typical rate at which you can produce photons using these quantum emitters depends on this spontaneous emission rate, which obeys the Wigner-Weisskopf formula. It's basically just a variation of Fermi-Golden rule. And the scaling is basically, in most quantum emitters, the scaling is going to be dipole squared times the frequency cube. So for the optical range of omega, you will have emitters that basically emit typically around 1 gigahertz, maybe a little bit less of a rate than 1 gigahertz. And here is a fantastic review of all solid-state single-photon sources that are available today. So one question so for those who are not familiar with this, the way we actually verify that the emitter or the source produces indeed single photons is using the so-called Hanbury-Brown Twist experiment. So we direct a beam of light at a beam splitter, and this beam splitter splits the optical beam amongst two bucket detectors. So these detectors produce a click every time a photon impinges on them, and the electrical signal from the detectors is routed towards a box which stores the detection events in time. And then the question you want to ask yourself is, do these detectors ever click together? So if they never click together, then you're sure that your beam is consisting of single anti-bunched photons. That's because a single photon cannot make two detectors go off simultaneously. That is why this experiment is a very efficient way and very easy way to check the single photon purity of your source. So I will use this experiment in the future slides. So this is called the Hanbury-Brown Twist setup. It's a very commonplace experiment in this area. Now, the question I'd like to reflect on is fundamentally how high of a speed can we produce single photons in quantum emitters? So the single photon production rate depends on the emitter's excited state radiative decay rate. For an emitter in vacuum, this rate, which again we label here as just gamma zero will be our intrinsic rate in vacuum. This rate depends again on the dipole square times the photonic density of states, which is proportional to omega cube, like we discussed on the last slide. And this is given by the Fermi-Golden rule. And this, the strength of the dipole and the photonic density of states basically together quantify the light-matter interaction, which is at play here. The radiative decay rate can be enhanced using the so-called Purcell effect in optical resonators. The Purcell effect takes into account the influence of two parameters. The first parameter is the quality factor, which basically quantifies how long the photons interact with the emitter as the photon bounces back and forth inside the resonator. The second parameter is the resonator volume, normalized by the diffraction volume. So the diffraction volume is simply basically lambda cube with some prefactor. And the mode volume indicates instead the spatial concentration of electromagnetic energy around the emitter. So these two parameters are important if we want to understand the spontaneous emission rate. So we naturally have two complementary strategies of enhancing light-matter interaction in optical resonators. In the case of the more traditional dielectric photonic resonators, such as photonic crystal cavities or Fabry-Perot resonators, the enhancement is based on large quality factors and diffraction-limited mode volumes. In the case of plasmonic resonators, so that's when you use basically metals to make a resonator, you use metallic nanostructures. In this case, the enhancement is basically the Q factor is rather small, from 10 to about 100 maybe, But because the light here has the opportunity to couple to free electron plasma in the metal, the achievable mode volume can be several orders of magnitude below the diffraction limit. So I should notice that the use of Purcell factor is debatable when applied to such open systems, but this reasoning is very intuitive, I think, and I will use it in the rest of the talk because it does provide you with the right physical intuition and it gives you the correct estimates for the trends. So it's very useful to still use this Purcell effect intuition based on Q over V, so quality factor over the mode volume. So to estimate the maximum achievable photon emission rate in the photonic case, we must calculate the limits on both the quality factor and the mode volume. So as the Q factor increases, the cavity resonance gets proportionally narrower. So that's normal. However, the emitter decays basically faster and faster. So it started with a rate gamma 0, but now as you add this Purcell effect due to the cavity, the emitter decays faster and faster, and therefore its emission line width basically broadens. At some point, intuitively, you basically reach a regime in which the spectral width of the emitter no longer fits into the cavity because the cavity line width shrinks and the emitter line width increases. So at some point, the emitter no longer spectrally fits into the cavity. This limit corresponds to the onset of strong interaction between the emitter and the cavity. And in this regime, we will witness something like maybe single atom lasing, but it's not really suitable for single photon emission anymore. So this strong interaction limit can be quantified through this inequality here. On the other hand, the mode volume, as we know in the dielectric resonators, is diffraction limited. So this naturally gives us this condition that V0 over V is less than 1. So consequently, the maximum achievable rate in the best case will be about 10 to 100 gigahertz. So this may seem like a very high rate. If we could produce single photons at 100 gigahertz rate, it would be quite remarkable. But unfortunately, things rarely get even close to this limit because of many technical issues. For example, the emitters can be thermally broadened, and then this limit will no longer include this radiative rate, but it will include the dephasing rate, and the limit will be much less advantageous than this. So we note here that this speed limitation dictated by diffraction limit, this gigahertz range, has another consequence, which is that we must cool the emitting dipoles down to cryogenic temperatures. So if we want to work with photonic resonators, with dielectric photonic resonators, we must do so at low temperatures. Because only then we can spectrally fit the emitters into this high quality factor dielectric cavities. In the plasmonic case, let's first examine the very simple case scenario where the cavity is just a single plasmonic nanoparticle. Let's describe the plasmonic material using the Drude model. So this model has two important parameters. One parameter is the plasma frequency, omega p, and the other parameter is the loss rate, gamma ohmic. Considering this metallic nanoparticle as our resonator, we're no longer subject to the traditional diffraction limit, but instead the main limiting mechanism becomes the photon loss in the metal. Specifically, the loss related, or the so-called non-radiative quality factor of a plasmonic nanoparticle is inversely proportional to gamma ohmic. So it's basically omega over gamma ohmic. That's going to be the non-radiative quality factor. In order to generate photons rather than heat, we must ask that the radiative quality factor is smaller than the non-radiative one. So photons must exit the structure before being lost. So that imposes a natural limit that the total quality factor of a plasmonic nanostructure has to be less than omega over 2 gamma ohmic. At the same time, there is the same condition imposes a limit on the mode volume of the structure. So specifically, if the mode volume of the plasmonic resonator is too small, then it doesn't radiate very well, and you will basically lose photons very efficiently in that structure because they will not have the time to exit before being lost. So that dictates a limit, fundamental limit on the mode volume for this specific metallic nanoparticle. When we just have one plasmonic mode, we will have this limit on the mode volume. So combining these two figures to produce the Purcell effect, the Purcell factor, we will basically find that the achievable enhancement in plasmonic systems is fundamentally much stronger than in the dielectric resonators by about 2 orders of magnitude. So now you're entering terahertz range. This limit that we just derived here, so it's actually from this paper here, pertains to a single plasmonic nanoparticle supporting, again, a single plasmonic mode. But we can note that there is a potential to do much better than that. A single nanoparticle must be small enough to offer strong electromagnetic field confinement, and at the same time, it must be large enough to be able to radiate photons faster than they're lost. In other words, it must act simultaneously as a cavity and as an antenna, which basically makes it fulfill two contradictory goals. And for about a decade already, we have seen the development of plasmonic systems featuring at least two different modes, one antenna mode and one cavity mode. An archetypal example of this is basically this Nanopatch antenna, where the emitter is embedded into the plasmonic gap between a film and a nanoparticle. The gap acts as a small size cavity, and the nanoparticle acts as an antenna that helps outcouple the radiation to the free space. So the function of the cavity is to enhance light-matter interaction, and the function of the antenna is to efficiently couple this system to the free space. So in this way, we can resolve the trade-off between field confinement and efficient outcoupling to the free space. Several groups, starting with Mike and Mikkelsen, have used such structures to enhance quantum emission. And 2 years ago, our group has embedded nanodiamonds with single nitrogen vacancy centers in diamonds. So these are atomic scale defects in the diamond lattice consisting of a vacancy and a neighboring nitrogen substitution. So you can have these defects actually in even very, very small particles. So in this experiment, we work with nanoparticles that are only 20 nanometers and cubes that are only 100 nanometers. So it's really highly subwavelength structures. And we have embedded these nanodiamonds with single NV nitrogen vacancy centers into these nano antennas. Uniquely, these nitrogen vacancy centers have very robust quantum emitters that can sustain very high excitation rates. And they can sustain these high electric fields that are present in these cavities. At the same time, the Nanopatch antennas were made out of crystalline silver. So this is the best plasmonic material to date, in my personal opinion, because it has a very high plasma frequency. It has lots of electrons, and yet it has very advantageous loss figure compared to other plasmonic material. Specifically, the epsilon double prime, the imaginary part of the dielectric permittivity, is close to 0.1 in the visible range, which is really, really much better than, like, let's say 10 times better than gold. So this SEM plot shows how the coupled systems look like. There's a silver film on which you have small white spots here that represent nanodiamonds with average size of 20 nanometers. Many of these nanodiamonds are empty, but some contain single nitrogen vacancy centers. Then in the middle, you see a large white square here. So that's the crystalline silver nanocube with a size of 100 nanometers. These nanocubes are randomly thrown around kind of everywhere on the substrate. And the substrate contains obviously millions and millions of these nanoparticles, both cubes and nanodiamonds. And every now and then you end up with a single nanodiamond containing a single nitrogen vacancy center that finds itself right under a single crystalline silver nanocube. As we scan the substrate using a confocal microscope, we identify such systems and we can measure their emissions. So here I show some data with two colors. So the blue curves correspond to a representative NV center in nanodiamond simply positioned on a glass substrate. So that acts as a reference. And the red curves correspond, so NVG stands for NV on glass, right? And the red curves correspond to NV centers coupled to nanopatch antennas, or NPAs. So we're really interested in this red data here. So we do see this characteristic autocorrelation dip, which is obtained from this Henbury-Brown Twist experiment. And the dip shows that detectors basically don't click together. They don't click with a delay time between them of 0 nanoseconds. So that means they tend to not click together, and that is symptomatic of single photon emission. As soon as you see a dip like this, this tells you that there is some kind of non-classical emission going on in your coming from your nanostructure. So we see that the NV centers on glass feature very broad anti-bunching figure, but in the NVs coupled to nanopatch antennas, this autocorrelation dip is very narrow. So this indicates that we have a basically much faster emission going on in these NVs. And indeed, when we actually measure the fluorescence decay from both structures, we see that there is a difference of about 100 times in terms of emission speed from NV centers on glass and NV centers in these nanopatch antennas. And also, we see 100 times increase in brightness. So basically, this speed up happens without penalizing the efficiency. That's what it means. So all this speed up goes into producing photons rather than producing heat. That's what it means. And indeed, in this experiment, we saw these NV centers coupled to nanopatch antennas emitting very high photon rates, up to 35 million counts per second, already accounting for, already with the subtraction of the background. So by subtracting the background, we see 35 million counts per second, which I think to date is still the highest single photon emission or detection rate from a room temperature quantum emitter. Now, we see here that the spectra of the emission are extremely broad. Basically, the NV centers themselves have a native spectrum of with a width of 100 nanometers. And we work at room temperature, so that's why the spectra are so broad. And you see that even though the spectra are extremely broad like this, we still can have 100 times enhancement with these plasmonic nanocavities. So the cavity antenna systems.
Yeah. There is a question from Paul.
Yeah, great.
He asked, he asked, is this with CW or pulsed pump?
Oh, this was with CW, yes. So these high counts, yes, they would be lower if we worked in pulsed regime, but in CW, that's what you get, yeah. The cavity antenna systems, such as nanopatch antennas, look quite promising as they do achieve a broadband enhancement of single photon emission at room temperature, again by about a factor of 100, using very cheap random assembly approach without any geometry optimization whatsoever. Nevertheless, even from the earlier analysis, it's clear that in our experiment, the structure operates very far from its fundamental limits, because we're expecting something like terahertz scale rates, and we're getting something like maybe 10 gigahertz or something like that. So we do expect that these systems can work much better, but how much better? So what is the fundamental limit for these cavity antenna systems? And how to reach this limit. So for this, we must do a slightly finer analysis, but using the same underlying ideas as we discussed earlier. Specifically, we consider plasmonic systems where the quantum emitter is coupled to a smaller cavity mode A1 with mode volume V1, which in turn couples to a larger antenna mode A2 with volume V2, and finally to the free space. So we assume that these modes are hybridized. So in most structures, this is a reasonable assumption as they are very close to each other. So they are basically, these modes are hybridized through dipolar interaction, and they are basically strongly interacting. We have recently studied the fundamental limits for quantum emission in such hybridized mode antennas. In the case of antennas made from epitaxial silver, these photon production rates can be extremely high, well into the terahertz range, as expected already from single nanoparticle analysis. But what's more, because of the impedance matching that the antenna mode provides for the cavity mode to radiate efficiently into the free space, because of this impedance matching, the plasmonic nanostructures, which are usually considered to be very lossy, can actually feature very low losses on the order of just a few percent. So here we show the far field photon production rate in color as a function of these adimensional mode volumes V1 and V2, which are divided by the diffraction volume. So V1 and V2 are basically adimensional parameters here, and we see that there is an optimum point in this phase space when V1 and V2 are equal to some specific values which are smaller, obviously, than V0, than the diffraction volume. And for these values of V1 and V2, we obtain the optimal far field photon emission rate. And for that particular configuration, we see that the photon emission efficiency, if we take into account the losses in epitaxial silver, these losses are just on the order of a few percent. And then we calculated the maximal possible far field photon emission rate from this kind of configuration, and we see that it has some kind of an intuitive formula here, but it basically depends on omega, which is the operating frequency of the dipole, omega p, which is the plasma frequency of the metal, which plays paramount role here. The higher the plasma frequency in the plasmonic nanostructure, the better things are, and gamma 0, which is the intrinsic radiative decay rate of the emitter itself. And so we see that we can get an enhancement of 1,000,000 times. And there are many works in the literature where this kind of enhancement can be seen from numerical analysis. But here we see that it's actually using just very easy analytical approach. we can get to the same limit, and we now have a full understanding of what's going on when we change the volumes. So we didn't even go into the specifics of the mode structures, of the configuration of these nanoparticles. Just based on simply this per cell analysis, we can get to the same figure as with numerical simulations. So the optimal volumes V1 and V2.
Simeon,
Yep.
There is another question.
Mm-hmm.
Can you see it?
Sorry,
okay,
I need to.
I'll read it for you.
Switch to chat. Mm-hmm. Does your detection equipment see all of the photons emitted? Isn't there still the problem of radiating into modes that you don't catch? Absolutely, that's true. So I will probably talk a little bit about collection efficiency later. I think I have some slides on this. But this is a big problem for all quantum emitters. You do not detect all the photons. So I would say that the typical efficiency of a confocal microscope, so we work with the confocal microscope configuration, the typical efficiency there is at most 10%. But this is due to the fact that you are not integrating your structures on chip. I think on chip efficiencies would be much higher than 10%. And I will talk about integration prospects for these sources down the road.
So how about the? I have a question related. How about the loss into basically the intrinsic loss, like conversion into heat? How does it compare to the gamma zero?
Yeah, so this is why we have this curve here, which shows the radiative efficiency, right, as a function of the mode volumes. So theoretically, the efficiency should be 96%. That means you basically get 96% of the photons out in the free space. The question is whether you can collect them or not. That's a different question. But theoretically, if you take into account the intrinsic losses in the metal, right, that's what you're asking. You should have an efficiency of 96%. And the reason why you can have this, even though your metal is so lossy, is again, the fact that in this structure, you have two different modes, one which enhances the light-matter interaction and the other one which acts as an impedance match for this sub-wavelength mode. So I think this is one way in which we can make plasmonic structures be low loss, even though the materials that they consist of are very lossy.
Okay, so it's roughly like 2 orders larger, gamma zero comparing to the intrinsic loss.
Yeah, indeed. And I think I actually have some simulations. Let me see if I can. Let me see if I can show you numerical simulations, because yeah, so I have some simulations here which show the total decay rate and the loss rate, and there is roughly 1 or 2 orders of magnitude between them, depending on the configuration, but it always stays at least 1 order of magnitude below. Again, this is theory, right? In the experiment, you will have lots of other things going not your way, but in theory, these structures can be, in my opinion, very efficient if we do it right. So these optimal mode volumes V1 and V2 that we found earlier at this location in the phase space, if they are represented as cubes, they will have sizes of 3 nanometers and 60 nanometers. So in our experiment, we have diamonds that are basically 20 nanometers in size and the cubes that are 100 nanometers in size. So we're doing really well on the cavity, on the antenna side. So the antenna is roughly optimal. But the cavity mode, of course, is much larger than it should be in the optimal configuration. So, of course, the natural idea to reach the optimum would be to work with much smaller particles, for example. But there are technical issues there. For example, if you make your nanodiamond extremely small, then the emitters become unstable. They start interacting with the surface, and you have to be a really good chemist to solve these problems. And it's not impossible. It's actually quite possible. We've seen stable emission from particles that are as small as 2 nanometers, but it's just an additional technical hurdle. So to just verify the practicality of these ideas, we decided to go another route. So what we decided to do is to assemble a nanopatch antenna with a single NV center, and then use a strong laser light to soften the cube and make it sort of sag on top of the diamond, which would modify the cavity side. So we apply CW laser pump at approximately 1 milliwatt, and the nanocube surface basically softens. We verified using a controlled AFM experiment that as a result of laser treatment, the height of the nanocube particle decreases by about 2 nanometers on average. So after the photomodification, we end up with a structure that has a different cavity volume than before. And the antenna volume does not change. So according to our theory, we should see an enhancement. So if we go down, so along this line, we go down in the cavity volume, but we don't modify the antenna volume, we should see basically the same efficiency, but we should see a faster decay rate, and therefore more counts per second. And that's exactly what we see. We do see that after photomodification, we see a further enhancement of single photon emission, and we see higher counts. So that means that we shouldn't be really afraid of small mode volumes with plasmonics. This confinement of light, even though we're confining the mode of the plasmonic cavity, we're still getting more counts per second. So this enhancement does not go into heat. It goes into producing more photons. So of course, this doesn't work every time because this procedure is not really very well controlled. Every once in a while, you kill the emitter by doing that. So the emitter just basically dies and bleaches away. Sometimes you see no modification at all because this modification process, as far as I understand it, is a threshold process. So you have to be on this fine line where you're modifying the antenna, but you're not melting it or something. This shows that it's possible to get higher photon rates by making smaller plasmonic cavities. I see that there is another question in the chat. How nice is the output mode? How well one couple into an optical fiber? I will actually touch on this. I will show you the back focal plane emission of this cavity. What is the photon frequency? Jim is asking. That's a great question. Here we work with nitrogen vacancy centers, which emit around 600, 700 nanometers. So it's a visible range, a red portion of the visible range. And the emission extends across the entire red portion of the visible range. It's basically 100 nanometers wide. So before and after photomodification, we do see the same autocorrelation features. So that means that this enhancement of emission is not due to background. It's really the single photon emission that we're enhancing. And actually, quite interestingly, we do see a red shift of the spectrum, as we would see from as we would expect from a hybrid mode. Actually, the spectrum shifts quite dramatically. It doesn't always happen like this, but in this particular emitter, it did happen. But we always see some, when we see these kind of features, we always see some kind of red shift for the mode, which basically indicates that we indeed changed the cavity. As you shrink basically the gap between the cube and the film, you do expect a red shift of the cavity mode. So I should say that in these experiments with nanopatch antennas, I would like basically to touch upon the integration aspect of these sources. Because of the random assembly method that we used in this experiment, the probability of successfully assembling a structure like this is extremely, extremely low. And things only worked out because a very large number of particles are present on the substrate. Then we are just lucky to have these systems self-arrange, just by pure chance. So even in the case of successful assembly, we still cannot precisely control the geometric arrangement of nanoparticles. And in any case, we certainly do not control the locations on the substrate where these structures appear. So let me change the slide. I'd like to emphasize a little bit the point about geometric control in these nanopatch antennas. So another practical differences between photonic and plasmonic resonators is that in the photonic dielectric case, we mostly have to align the coupled systems in frequency. But in the plasmonic case, the difficult part is to actually align them spatially. If you're realizing a dielectric cavity enhancement of a quantum emitter, you want the emitter to be exactly in resonance with the cavity, with a precision usually much better than 1 nanometer. However, a difference in position of something like 10 nanometers in space, in this case, will not affect the performance very much. In the plasmonic case, it's exactly the opposite. You don't have to worry about frequency alignment because the cavity and emitter are usually more broadband. But the spatial dependence of the enhancement that is represented here schematically with the pin curve is extremely sensitive to the relative position of the dipole and the nanostructure, sometimes down to single nanometers. So therefore, we'd like to have a more control in our realization of plasmon-enhanced single photon sources based on these nanopatch antennas. So we developed a method for assembling these nano antennas in a way that's close to being on demand. The method is very simple conceptually. First, we scan a glass substrate with candidate nanodiamond particles, identify promising candidates containing single color centers, such as this one, for example. Then we transfer these particles using the tip of an atomic force microscope to the epitaxial silver substrate. Then the idea is to deposit the nanocubes and push one of these cubes directly on top of the diamond. So this was the artist view. In reality, it looks somewhat like this. So you have a small fluorescent spot here. That I don't know if you can really tell that it's a fluorescent spot, but it does show anti-bunching feature in the autocorrelation, indicating it's a single photon emitter. Then this is this same particle found with the atomic force microscope tip. So it's about 18 nanometers high in this case. So it has suitable size for the assembly. Now it has disappeared from the substrate. So this diamond has been picked up by the AFM tip. This is the empty silver substrate. So the diamond is still on the tip. Now it has reappeared on the silver substrate. It still has about the same height. So we didn't really destroy the diamond particle. It's actually hard to destroy diamonds. And then this is a nanocube that fell right in front of this diamond. And we can push it, we can nudge it with the atomic force microscope tip until this characteristic this characteristic basically gradient on the upper surface of the cube appears. So you know that the cube has basically climbed on top of the diamond. And as you check the single photon emission, you see that there is a narrowing of the autocorrelation feature in the weak excitation regime. And this tells you that the NV actually successfully couples to the nanophotonic cavity. So now we can actually control the assembly location. We can partially control the relative nanoparticle positions, and we hope to further develop this process to increase its yield. We note that these nano antennas actually operate still very far from a fundamental limit, but as we showed, it's possible to optically modify these nano antennas and further improve their performance by shrinking the cavity modes. And of course, it's always possible to try to work with smaller and smaller nanoparticles to approach the optimal operation limits. So now answering Paul's question, so these nano antennas have a very, very serious drawback. This drawback is that the emission is very poorly directional. The mode doesn't look good at all. So this is the basically angular distribution of the emitted photons measured with back focal plane technique. And what you can see is that the emission in the upper half plane is basically isotropic. This poor directionality can be mitigated using additional nanostructuring. Like, for example, in this paper, they used basically rings, plasmonic rings around the structure to demonstrate better directionality. However, even in this case, most of the time, the analysis will be still done in the out-of-plane configuration, which is not really, something you want for a device. So we can't yet say how promising these nano antennas are to realize on-chip sources of photons. But there are definitely structures that realize very good on-chip photon collection efficiency. For example, photonic waveguides. These are just a couple of examples in recent years where people have embedded single color centers in diamond into diamond waveguides, or plasmonic waveguides for that matter. So the common feature of all these methods is that you have a very good collection efficiency typically, because that's on-chip configuration. So obviously you can collect much better on chip. But at the same time, the enhancement of the radiative rate is usually very, very modest. So from 1 to about 10 times. So we wanted to ask ourselves whether it's possible to have the best of both worlds, have good collection efficiency and at the same time, high enhancement factor. This is something that you cannot have in waveguides, because in waveguides, you don't have this confinement that you need to enhance the emission line. Actually, I should notice that there is also another approach based on hybrid structures where you have a photonic cavity, like a whispering gallery mode here, right? And then you have a plasmonic nanostructure which sits on top of that. And if you tune them correctly, if you tune these systems correctly, then you can sort of take advantage of the photonic enhancement and plasmonic enhancement. Now, it's going to be still a narrow band approach, but it's a very interesting kind of structure that was explored theoretically, at least. And there should be experimental results coming from Fimius Kundering group at Amolf in the Netherlands coming soon, as far as I know. So this is really an interesting structure to follow the development of. So what we propose is a simple plasmonic structure that we call a quantum plasmonic launcher. And that demonstrates the potential for having both high enhancement factor and preferential coupling into on-chip surface plasmon polariton modes rather than free space photons. And it's realized by growing first an optically thick epitaxial silver film. Then you position nanodiamonds on top of this film and you cover them with a second layer of silver that is polycrystalline in this experiment. So it's not really ideal, but the big advantage is that you can couple all the nanodiamonds on your substrate with just single deposition step. So it's automatic coupling. And at the same time, so here you see we milled a groove around this, this emitter just to outcouple and collect the radiation using the objective. But the real strength here is that in down the road, what you want is not having a groove like this, but to basically adiabatically couple these plasmon polaritons into low loss dielectric waveguides. So then you can ensure very good efficient collection, and at the same time you will see a very strong enhancement with this kind of plasmonic cavity. So intuitively the way it works is that you have a small cavity mode, but you don't have a dedicated antenna mode. So this plasmonic cavity does not couple to free space very efficiently. Instead, so because of wavelength mismatch, it's not going to couple to free space as efficiently as a Nanopatch antenna. But the SPPs have a smaller wavelength, so this cavity will actually preferentially couple to these surface plasmon polariton modes. And then again, the idea is that these surface plasmon polaritons can be adiabatically converted into a low loss waveguide. This is something we didn't do in this work, but this is something that we certainly envision how this can work down the road. So I'm not going to go through details because I think I'm running out of time right now. But I'm just going to show you that this structure has been experimentally realized. We saw that the total efficiency for this structure is still very low. It's 2.5%. And this is primarily because of the quality of this top silver layer that is really hard to control. But if it's replaced with a better plasmonic material, I'm sure that this loss figure will go up dramatically. But right now it's really not high. However, this structure indeed generates preferentially surface plasmon polaritons rather than free space photons based on this branching ratio here. And one interesting thing about it is that in the CW excitation regime, we don't see any autocorrelation features at all. So you may think, well, we don't have single photon emission, but we actually do, because if you excite this with a femtosecond laser, you start seeing dips in the autocorrelation. And this indicates that the lifetime, the fluorescence lifetime is very short. And indeed, when we measure the fluorescence lifetime, it's actually below 10 picoseconds. We do have a lot of counts from this structure as well, not as much as you would expect for a fluorescence lifetime like this, but that's the problem of efficiency actually that I just mentioned. So there's still a lot of work ahead trying to make these structures efficient, but at least in theory, we know how to do this. And in the experiment, it all comes down to correct engineering of this plasmonic volume that is adjacent to the emitter. This is where most of the losses typically happen. And so this paper just came out this year, very recently. And in do I still have a minute, KJ?
Yeah, you can. Yeah, a couple more minutes probably.
Cool. So I'm just going to show another kind of curious point on integration. So I mentioned that these nanostructures can be assembled in principle deterministically by transferring the diamonds. And with my colleague Jacques Kudyshev, we asked ourselves, well, can we actually can we speed up this transfer process by accelerating the single photon characterization of quantum emitters on the large scale, so that we can basically just scan a substrate and immediately see which are the single photon emitters and which aren't. So usually this requires this autocorrelation Henbury-Brown twist experiment where you split the beam between two detectors, right? And then you correlate the counts. But this is actually an extremely slow measurement typically, because when the particles are just on the glass substrate, they don't emit a lot of photons. And what's more is that these correlation events are much more rare than just photon clicks. So you need 2 photon clicks on these detectors to produce 1 correlation event, then that you later bin into a histogram. You basically present it as a histogram, and you see how often these detectors click together at time delay 0, and how often do they not click together, just basically with some time delay tau, right? So you have to accumulate this histogram, which consists of co-detection events, which are much more rare than just single detection events. And so typically to accumulate a good size histogram, you need on the order of minutes for every single photon emitter that you try to analyze, right? So to find single photon emitters is an extremely slow process, actually. And then typically when you have a histogram, so if you basically have this autocorrelation that falls below 0.5 at 0 delay, you could heuristically call it a single photon emitter. And if it's larger than 0.5, it's not single. Now, it doesn't mean that 0.5 is a good figure of merit. Of course, this threshold can be changed. It could be, if you're very restrictive, you could set this threshold not at 0.5, but at 0.1. But the point is that you have to basically classify, you have to decide whether you want to work with that emitter or not. So typically what you do is you fit the histogram using Levenberg-Marquardt fit, by exponential fit, and then from that fit you retrieve the value of this autocorrelation at 0 delay, because in the presence of noise you have to do this fitting to make this decision. But it turns out that machine learning can be very, very efficient at this, and you can indeed make a decision very, very quickly and identify the single photon emitters within 1 second. And here I just very quickly, I present these results. So if you do conventional fitting on data sets with integration time of 1 second, this conventional Levenberg-Marquardt fit performs no better than random guessing. It's basically 50% accuracy on average, 53%. But machine learning methods perform much, much better, and they can ensure an accuracy of over 90%. And this is just one technique that can be made to accelerate and to scale up these assembly methods for these plasmonic devices. I think in the future, it's possible to extend these machine learning methods to many other measurements, including actually the assembly process itself. And this is something I would really be excited to try. And if there are specialists who know how to proceed with machine learning and basically teach an atomic force microscope to assemble these plasmonic devices, I would be really interested to talk to you and learn a little bit more about this field. So with that, I just would like to conclude and also say that more broadly, plasmonics offers an alternative path for the development of quantum photonics, because it also offers the potential to address the issue of quantum decoherence. In order to produce indistinguishable photons, we must ensure that the emitter stays coherent for the entire duration of the emission. So you want to get rid of these dephasing events within the photon's wave packets that are caused, for example, by elastic interaction with phonons. And the more traditional dielectric photonics approach relies on high quality factors and cryogenic cooling to extend the coherence time of quantum emitters. And as the dipole coherence time increases beyond the spontaneous emission rate, that's where you get indistinguishable photons that can be really applied in quantum information. But plasmonic resonators, on the other hand, give us the opportunity to operate at much faster speeds, and therefore we can start tolerating much higher decoherence rates than before. So we can open access to larger classes of quantum systems that would be otherwise disqualified for having too short of a coherence time. But the downside is the presence of optical loss, obviously, in plasmonic nanostructures that we just outline a strategy for basically to improve these losses. And the vision is to have ultra-fast femtosecond scale photons propagating in quantum networks, and such photons, we would be able to pretty much confine them to very small mode volumes and make them hopefully in the future interact with one another if we have sufficient nonlinearity. And so I think that there will be definitely advantages in using plasmonic devices to gain higher bit rates and possibly have new technologies for realizing photonic gates, but also efficient transduction to other platforms for quantum information. So I will stop here, and I will welcome any questions, obviously, and I really thank you for your attention.
Okay, thank you for the interesting talk. So there is a question from James.
Mm-hmm. Has there been a study of E and B field patterns in the vicinity of the emitter and throughout the volume of the silver nanocube? Yes, Yes, absolutely. Every time we do, I didn't show really numerical simulations here, but every time we do an experiment like this, we do a full simulation, full wave simulation of what's happening in the vicinity of the structure. So we try to make designs that are conformal to the predictions of these numerical simulations. So we actually have a pretty good idea of what happens with these E and B fields. I would say that the E field is more important because the electric dipole here in these emitters interacts with the electric field, not with the magnetic field. But I also have some portion of the talk that I wanted to do, but I didn't have the time to talk about the spins and also the magnetic interactions.
So I guess I was just thinking in the vicinity of a metal, usually the magnetic field is much larger than the electric field because of the screening that happens. And there's a phase difference between the electric field and the magnetic field, and electric field in a wave that comes up to a metal surface. And I guess what I was wondering here was, does this pattern extend around the edge of the currents and the magnetic field extend around the edge of the cube that you were showing us there and actually face out towards free space? Or is it all in that region between the silver substrate and the silver cube that's sort of trapping it, trapping
Yeah, I think I got your question. So I'm going to illustrate here. Unfortunately, I don't have a picture of the fields with me right now, but basically most of the field will be in here in the gap. This is where the enhancement happens. You know, you have fields that are basically 10 to the 2 times larger than the fields in vacuum. So very high fields in here in the gap, right? But the antenna also has some of this, so also provides some of this enhancement. So you do see basically strong electric fields all around the nanocube, right? But they're especially strong in the gap. Okay. And the field is directed from one surface to the other. So the field it's perpendicular to the surface basically. So you want the emitter also to be aligned along that direction as well. So this is something I didn't mention, but obviously the assembly of these structures requires you to have the proper alignment of the dipole with your electric field in the cavity. This is something we don't quite yet know how to do, but what you want to have is a dipole that is vertical here, and because the electric field is also vertical. And the magnetic field, to answer your question about magnetic field, actually in the optical range, so in the microwave range, what you're saying is true. In the optical range, I would argue that the magnetic field is actually not enhanced near the metal. The mechanism for enhancing the electric field here is that you have additional kinetic energy of the electrons in the metal, right? Which allows you to store the excess energy from the electric field. So basically the cycling of energy between E and B is no longer balanced here. So you have much more energy stored in the electric field, and only a small portion of that goes into the magnetic field at the half cycle. Instead, the larger portion of electric energy goes into the kinetic energy of electrons. So that's the mechanism for enhancing the electric field here in plasmonics, in the optical range. Okay. So the B field is actually not enhanced to my knowledge. But however, the metamaterials, I should say, the metamaterials and plasmonics in general offer concepts to enhance this magnetic field. And then you have to work with, you know, ferromagnetic structures where mu is negative, for example. You can enhance, you can enhance the magnetic fields rather efficiently there. And you can have this, you know, magnetic version of metamaterials that would work maybe at microwave frequencies.
So I'm curious, how do you benchmark the machine learning method?
Oh, that's a great question, yeah. You mean how do you compare the accuracies, right?
Right. Basically, you're measuring, for example, the same emitter, then you're saying the machine learning method is, you know, is better in identifying it as a single.
Yeah. So to answer your question, we had a collection of many emitters, right? And we had acquired a lot of data sets, 1 second long data sets from all these emitters, right? But in addition to that, we also perform the ground truth measurements for the G2 on every emitter. So we actually know whether this emitter is basically below the single photon threshold or above the single photon threshold. This by threshold, I mean this 0.5 value. So this is the decision boundary for the classification. So what you want to learn is whether G2 is below 0.5 or above 0.5, but in the presence of high noise. So imagine that you know the actual values for G2 for all these emitters. So this is your ground truth. And then we train the machine on some of these data sets, and we verify the classification on other data sets, which the machine has never seen. And then you basically try to measure in how many cases for the testing data set, and how many cases the machine guessed right versus guessed wrong. And this is how we measure this accuracy.
Okay, then my question maybe is how do you determine whether the machine guessed right or wrong?
Yeah. So
what's your criteria?
Yeah. That's I didn't do a very good job explaining this part. So you have a noisy measurement. You have a noisy measurement for a specific quantum emitter, but for this noisy measurement, you actually know the ground truth, which is whether the G2 of this particular emitter is below or above 0.5, because you measure it separately.
Okay, I see. And so you already did a long time
yes.
measurement to determine.
Yes.
Okay.
Yes, we did the long measurements for all the emitters, so we do know the ground truth for every emitter, and therefore for every data set that we feed to the machine. And then when the machine performs the guess, we can compare these guess to the ground truth that we measured earlier.
Okay, I see. Thanks. Is there any further questions? Okay. If not, let's thank Simeon again for the very nice talk.
Well, thank you all very much for your time. And thanks, KG, for organizing.
Thank you.
Thanks, Simeon. It's really interesting stuff.
Thank you, Jim.
Yeah, talk to you later.
Yeah, talk to you later. Thanks, Paul.